Welcome to lecture number 55 of the course on nonlinear structural analysis, theory and applications. So, let us recall what we have done in the previous lecture. So, in the previous lecture, we have derived the theory of displacement controlled analysis technique. Okay. We have looked at one method which we are calling method 1, and then we have also done some simplification of that method. Okay. And we have seen one example briefly in OpenSys. The file is already shared with you. You can go ahead and take a look. And throughout the course, we have done displacement control analysis many times. There is just one simple command, okay, which I will show again, where you have to specify the node number and the degree of freedom and the incremental displacement. Okay. So, that is all what we have to say to OpenSys to be able to do the displacement control analysis. Okay. So, in this lecture, what we will do, we will talk about little bit about pushover analysis, which is a popular nonlinear static analysis used in the field of earthquake resistant design of structures. Okay. And then we will make some remarks on the method 1 that we have studied, or the simplified method 1. Okay. The remarks will be applicable for both, and then we will talk about method 2, which is the generalized displacement control technique, and we will also talk about work control technique. Okay. So, if you recall, we have done load control, then displacement control, okay, where we are controlling displacement of a 1 degree of freedom, of a single degree of freedom in a complete structure, and then we will talk about generalized displacement control as well as work control. Okay. So, let us get started with pushover analysis. So, what is pushover analysis? It is basically a nonlinear static analysis. Okay. And as you know, when you are taking a structure and pushing it, okay, you are going beyond its capacity. That means you are interested in the post peak response as well. So, a load control technique cannot be used. So, you will have to use a displacement control technique. So, what it is used for? It is used to study the lateral load resistance of frames that are designed to resist seismic loads, okay, typically in buildings. So, it could be moment resisting frame, it could be braced frame, it could be reinforced concrete, could be steel, could be, there are so many different types of lateral load resisting system that I briefly discussed in one of the previous lectures. Okay. What we do typically, let us say if I draw a frame, okay, a multi-story frame, right. Let us say this is a braced frame. Okay. So, it is something like that, an inverted V braced frame, right. So, what we do, we apply the gravity loads whatever is coming onto this depending on its tributary area, because in a building floor plan you will have gravity load resisting system and lateral load resisting system, right. So, this will take its own share of the gravity load based on the tributary. So, we apply that so that the P delta effect can be incorporated, and then we apply a lateral load profile. So, at each floor we apply some reference load values, right. Now, this structure has many degrees of freedom. Okay. It is not simply a 3 degree of freedom problem because we have 3 story. No, it is not. Okay. It has many degrees of freedom, where my reference load vector is basically a vector with all zeros except there are 3 non-zero entries corresponding to this degree of freedom, this one and this one, right. Now, what are these values? Well, that depends how you are doing the pushover analysis. So, this number could be based on your lateral load profile that you have used to design the structure, okay, for earthquake resistant design, or it could be based on your fundamental mode shape, which I will discuss in just a little bit. So, there are 3 entries here which are non-zero and has some values, right. Then what you are doing, we increase this lateral load proportionately. That means I am multiplying this load by a load factor, and what is that? That is my delta lambda for each load step. Delta lambda is what we discussed in the previous lecture, okay, or lambda, which is the cumulative value, okay, that we will get from the analysis, right. So, lambda times this reference load vector is my applied load k at a given step. So, we increase this lateral load monotonically by controlling the displacement at a suitable degree of freedom. Now, coming to this problem, we can decide, okay, I will control the horizontal displacement of this node, okay, or you can say I will control the displacement of that nodes, right. So, for this case, if there is no buckling of braces, then there is no problem typically, but the moment the braces starts to buckle, then you may have some convergence problem, and you have to see how do you control the displacement degree of freedom, which I am not getting into, because then I will not be able to complete the syllabus that I wanted to cover in this course. Okay. So, you have to choose the degree of freedom appropriately, and I will make some more remarks on that. Then once the analysis is done, what we do is study the base shear versus roof displacement. Now, what is base shear? At a given instant of time or at a given load step, this reference load vector, which are these values, multiplied by that lambda, if you add all of this, so that is my base shear. And then I look at the roof displacement. So, typically base shear versus roof displacement is studied. If it is a moment resisting frame, we study the formation of plastic hinges, which I can call simply limit state, or if it is a brace frame, I can study how the braces are buckling, what is the sequence of brace buckling, and many other things can be studied, right. So, basically the idea is to study the lateral force resistance of a seismic resistant lateral force resisting system. Okay. Now, how do we create the model? Well, that is what we have discussed throughout this course. So, we have two sources of nonlinearity, material and geometric. Now, material nonlinearity, we can take one of the two approaches. We can use concentrated or lumped plasticity model, where I am modeling the plastic hinges at the appropriate location in the structure, okay, if it is a moment resisting frame. And we can also use the distributed plasticity model. It can be displacement based element, it can be force based element. Okay. So, we create that, and then we have to account for the P delta effect. So, you can do a second order simplified P delta analysis, where in OpenSys you just turn on the P delta geometric transformation, or you can do a large displacement analysis as well, depending on what is your analysis objective. Okay. Now, if you look at this FEMA document, that is FEMA P695, it says, in general, pushover analysis shall be performed following nonlinear static procedure of section 3.3.3 of ASCE or ACI 41.6, okay, 4106, which I will show you the complete reference at the end. Okay. And then FEMA P695 says that the lateral force that we are applying, okay, let me draw the structure again. This time I will just draw a moment resisting frame. Okay. So, these are my forces that I am applying, right. Let us say this is F1, F2, F3 and F4, right. So, my reference force vector is basically a vector where I have many entries, and then this F1 may be sitting here, F2 and so on, right. So, what is this pattern? We call it a pattern, right. So, this FEMA P695 says that Fx, that means the force at any level x. So, let us say here this force is proportional to the mass of that floor, okay, times the ordinate of the fundamental mode at that floor. So, that means basically what I am doing, I am pushing the structure in its fundamental mode, right. So, mass times the ordinate of the fundamental mode. Now, what is fundamental mode? I have not discussed any dynamics yet. Okay. So, in the last topic of the course, I will briefly discuss about the fundamental mode, mode shapes and eigenvalue problem, and how do we solve the nonlinear dynamic problem in some detail. Okay. And then you will see what is the fundamental mode, right. So, for the time being, what if you are using OpenSys, what you have to do? You have to do an eigenvalue analysis in OpenSys to get the mode shape, and from there you take the fundamental mode, that ordinate multiplied by the mass, that is the force that you are applying. Remember, these are all reference values. We will be multiplying them by the scale factor or the load proportionality factor that comes out of OpenSys analysis. Okay. And then what you do? You plot the base shear versus the roof displacement, and you can get a curve like that. Okay. So, where FEMA P695 defines that the maximum value is Vmax, the maximum base shear capacity, and the maximum roof displacement or the ultimate roof displacement is defined corresponding to a 20% strength loss. That means, if you keep pushing it, you attain the peak and then it is going to drop. Okay. So, this drop up to what point you consider that ultimate, because this will be used in the further analysis. So, it says 0.8 Vmax, right. Now, how do you use this result in assessing the performance of your lateral load resisting system is beyond the scope of this particular course, okay, which is typically the topic for our earthquake resistant design course. Okay. So, for more details you can look at this document as well as the FEMA document. Now, as far as examples of pushover analysis is concerned, if you Google in OpenSeas, there are lots of pushover analysis examples available, but they are in TCL, not in Google Colab or in Python. But if you spend little bit time, you should be able to convert TCL to Python, or you can directly use the TCL, where you have to download the OpenSeas.exe and then use the TCL. So, that is also possible. Okay. So, since the examples are readily available, I am not going to do any example in this course. Okay. So, now let me focus on the method 1 and make some remark, right. So, if you remember, in method 1, we have to choose a particular degree of freedom at which we are controlling the displacement, right. So, it requires a proper selection of the controlling degree of freedom. Why? For some problems. For example, here I am taking this problem from this paper by Professor Powell and Simons. Okay. This is kind of an asymmetric truss arch. Okay. You see, this span is different from that span and it is loaded by P. That is it. Loading is also asymmetric, right, and the dimensions and other things are given. So, the objective is to determine the force versus the displacement, right. So, now when the analysis was done by controlling the displacement of this node, vertical displacement of this node, which is called delta 18, then the solution was going like this, and it stopped here, failed to converge after that point, right. Now, if you notice, something interesting is going on here. This is the solution after that step. So, it is called a snapback, which I will discuss more in just a little bit. But when they use the vertical displacement of this node as the controlling displacement, which they are calling delta 26, then they could get the complete solution for the load versus delta 26. Okay. So, now for this case, if you plot the load versus this displacement, then you will be getting that response. Okay. So, this tells us that you have to be careful about selecting the appropriate controlling degree of freedom whenever there is a snapback kind of problem. Okay. So, let me talk about that in just a little bit. So, in this case, you can see it fails to converge in a snapback problem. How do you handle this? Well, you need to adopt procedure that includes all displacement, or you choose the degree of freedom carefully. Okay. So, rather than using a single displacement component, we can include all the displacement. How? Well, using a work control method or a generalized displacement control method, which I shall discuss, or you can use arc length method, which is the next topic. Okay. So, now snap through versus snap back. So, from this paper by Crisfield, I am taking a general load versus deflection relationship, which looks something like that. Okay. Now, in this case, if you are doing a load control analysis, so you will go like this, and then here there will be dynamic snap under constant load, which we have already seen, then it will go like that. But if you do a displacement control, well, you will be able to track this you have already seen, right. But the moment you come here, after this point, the displacement control will give you a response like that, because what is happening here? Well, the displacement is reducing and so is the load. The load and displacement both are turning back and then again increasing. Okay? So, this is called snap back. Why is this happening? I will give you an example, right. So, in this case, if you use displacement control, then it will come down like this. At the same displacement, the load will drop and it will go like so. Okay. So, when do you get this kind of snapback? Snap through you have already seen by the 2 element truss. Okay. So, when do you get this snapback problem? So, let us consider we have a bar which is subjected to compressive load, okay, and a portion of the bar is buckling locally. Okay. That is what we are assuming, right. Now, this is called unbuckled portion. Local buckling is happening here. When the unbuckled length is very short, that means it is buckling something like this. So, this is my unbuckled length, right. The entire bar is buckling. Then the force versus deformation relationship is something like this. There will be a gradual decay or gradual reduction in strength the moment it buckles, right. What is this plot? So, this is basically the load versus the displacement r, which you can say, okay, if this is restraint, then this displacement of that point, right. So, for short unbuckled length, strength loss is progressive. But imagine if this is large, okay, and this is very small where buckling is happening. Then what happens? You get a behavior like that. Now, how do we obtain that behavior is what we are going to discuss. Okay? But why is this happening? Why is the force displacement curve turning back? Okay? Let us discuss. So, when buckling happens, there is a drop in the capacity, right. So, the moment there is a drop in the capacity, then this portion which is remaining elastic has to unload elastically. So, the moment there is elastic unloading, it was earlier compressed, now it should extend. Okay. So, now these two portions are extending and this is compressing, right. So, when this is large, so the extension is also large, right. So, when the extension is larger than this shortening, then what happens? Well, then the total displacement of this point basically turns back like this, right, because this shortening is smaller than the extension of this, which is associated with unloading, because the moment force reduces, this has to unload, right. When that happens, when you have this part large, I will show you an example which I created. Okay. So, for long unbuckled length, load deflection curve can turn back on itself. That means this behavior. So, this reversal occurs when for any given shortening delta in the buckled region, that means let us say this shortening in this region is delta, okay. The strength loss corresponds to an extension in the unbuckled region which exceeds delta. That means this extension is exceeding delta, then you get that behavior. Okay. If you use a displacement control technique to solve this problem, then the behavior that you will get, it will come here, then there will be a dynamic snap under constant displacement, and then again you will track this path. So, this path will not be tracked if you use a displacement control technique. Okay. So, I will demonstrate with an example, right. So, the snap through and snap back problems are some of the most difficult nonlinear problems in structural analysis. It can occur in thin cells due to geometric nonlinearity. So, in thin cells you can have local buckling where you can get a snapback or snap through type of problem. In concrete structure, due to strain softening response, which is a material nonlinearity, you can get this kind of snap through or snapback problem. If you look at this reference, you can get more details. Okay. Now, I wanted to show you this problem, okay, using a simple structure, right. This is my structural system. If you remember, in the previous lecture we have used this part, right. Now, what I am doing, I am adding a third truss element having the same length, okay, and having different cross sectional area and different modulus of elasticity. So, I am saying this is A1 E1 L0, this is also A1 E1 L0, but this is A2 E2 L0, right. Now, you can use same E for both, but have the area different. Let the area be different. Okay. So, that is what I have written. Member AB, BC have the same material and same cross sectional area. Member BD has different material and different cross sectional area. Okay. So, the objective is determine the force displacement response R versus R2. So, there are 2 degrees of freedom here, R1 and R2. Remember, these are all truss elements, right. So, this node can only go in this direction or upward. Now, I am applying a load downward. Okay. So, this is one DOF and this is the other DOF. So, this I am calling R1, this I am calling R2. Okay. Now, moving forward, let us define a relative stiffness parameter beta. What is beta? Is A2 E2 divided by 2 times A1 E1. So, this is A1 E1, I am just doubling it for 2 members, and this is A2 E2. This is just a definition, right. So, what happens when beta is large? When beta is large, that means this member is very stiff, right. When this is stiff, then what happens? Well, this reduces to a 2-member arch that we solved earlier. So, that means for large stiffness, this will show me a snap through behavior if I use a load control analysis, right. The behavior is going to be same as what we have done for this 2-member arch or truss. Okay. But when beta is small, that means what? This is much more flexible compared to that. Okay. Then what happens if I control this? You will see we will get a snapback behavior. Okay. When this buckles, right, it's just like the local buckling. This is buckling and then this member has to unload, and when it is flexible, the extension of this due to unloading is going to be more than that, and you will get snapback behavior. Okay. So, for large beta, snap through under load control, for smaller beta, snap back under displacement control. Okay. So, I have created an OpenSys example which I will show you in just a little bit, but before that, let me show you the result that I have generated from my own coding in MATLAB. Okay. So, this is for beta is equal to 5, which is relatively large, for theta 0 is equal to pi by 3, this angle. Okay. Now, whether you control R1 or you control R2 does not matter, you get this behavior if you are using a displacement control technique. If you use a force control technique, it will go like that and it will keep on increasing, right. On the other hand, if I reduce the beta by a factor of 10, that means this is now flexible. Okay. So, then what happens if I use displacement control using R1, that means this DOF vertical displacement, which is increasing all the time as I am applying this load vertically downward, okay, then I get the red curve, right. So, I get this kind of behavior. But if I use this R2, then what happens? Well, this green is the solution, it will come like so and then it will keep going like this, right. So, at a constant displacement, so this is the maximum displacement here, then it goes like that and like this. So, that means what is the takeaway? The takeaway is when you do a displacement control analysis where the displacement of a degree of freedom is controlled, that displacement must increase monotonically, otherwise you cannot get the actual behavior. So, in this case for R1, this displacement is increasing monotonically, but what is this plot then? Well, this plot is for R2, R2 divided by L0 sin theta 0, which is this height. I am just plotting the normalized value of R2. Okay. So, that shows this kind of behavior, right. Now, if I take different values of beta, okay, you can see all different kinds of response I can get, and I have determined all of this by controlling the R1 using the Newton-Raphson algorithm, Newton-Raphson iteration technique with the algorithm that I covered in the previous lecture. Okay. So, now let me show you this in OpenSys. The example is already shared with you. So, this is the structure. Okay. Now, let me show you first where is the reference load applied. So, this is my structure node 1, 2, 3, 4, and this is element 1, 2, 3, all are co-rotational truss element. At node 4 in the vertical direction, I am applying the reference load. At 4 in the negative y direction, I have applied P. Okay. And then for the controlling DOF, I have node 4 vertical direction and node 2 vertical direction. So, node 2 vertical direction is my R1, node 4 vertical direction is my R2 according to this notation that I discussed, right. If I show you the analysis, here is what I am asking, give me the value of beta. So, beta is A2 by 2 A1. In the slide I have defined A2 E2 by 2 A1 E1, but in OpenSys I kept this equal, hence it is A2 by 2 A1, okay. And controlling DOF is R1 or R2. So, right now beta is 0.5, controlling DOF is R1. So, I expect this kind of behavior. Now, here I am plotting R1 versus the force as well as R2 versus the force. See, R2 is showing this behavior, okay, and R1 is increasing monotonically, right. So, therefore, when I am controlling R1, there is no problem. But let me go back up and change the controlling degree of freedom. So, if I control R2 and rerun the analysis, what do you get? Well, you see that the R2 displacement is actually showing you a dynamic snap at a constant displacement, the load is dropped and then again it is increasing, and similarly R1 is accordingly obtained, okay. So, if you control R2. Now, if I change this beta value to 5, okay, and run this analysis, then it does not matter what you are controlling, okay. So, that is the key idea here, okay. So, I am also plotting the normalized displacement R by H for both R1 and R2. In this case, both are increasing monotonically, so no problem. But the moment you change the beta, then you will see if I do 0.5 and control R1, okay, rerun it and show you the result, you see that R1 is increasing monotonically, the blue, but R2 is not increasing monotonically. It was increasing and then there is a reduction and then again increasing. So, therefore, if you control R2, you will have that snapback kind of problem, okay. Very quickly, what is generalized displacement control technique? So, the idea is instead of controlling a single degree of freedom, one can control a generalized displacement delta Rg, which comes from these references which are listed at the end, okay. So, G stands for generalized. So, I am saying I am controlling a generalized displacement, okay, and how do I get that? Bg transpose is a row vector multiplied by all the displacement, okay. So, if I write after taking transpose, so this is n cross 1 and this is 1 cross n after the transpose, right. So, Bg is any convenient vector. So, let me give you an example. So, let us say if I take this structure, so this is a beam column element, here it is a roller and here it is a guided roller, okay. So, it is like this, it is a guided roller, it offers only moment restraint and the horizontal restraint, here it is only the vertical restraint. Is it stable or unstable? It is a stable structure, okay. So, I have discretized it into many elements. So, 1, 2, 3, 4 elements. If you number the degrees of freedom, this is R1, R2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and this is 12, right. So, now let us say in this example, if I want to control the delta R1, this degree of freedom, then what is my Bg vector? Well, it is 1 and all 11 zeros, because there are 12 degrees of freedom. If I want to control this, then what is my Bg vector? All zeros except the last entry unity. But I can also control, let us say, delta R1 minus delta R12. That means kind of going in this direction and that direction, what is the difference? If I want to control that, then I can set my Bg, first entry is 1, then 10 zeros and then minus 1. Okay? That is the idea of this generalized displacement control, which I am calling method 2. Okay? Now, how do we do this? Well, again, what we have used earlier, the incremental displacement is load proportionality factor multiplied by the displacement increment due to reference load plus the displacement increment due to unbalanced load. If I substitute that in this equation here, then what do I get? I get that. Now, in this equation, I have this is known quantity, this is known quantity, this is known, this is known. I can easily calculate what is my delta lambda, right? So, for the first cycle, this is approximately 0, okay, because nth load step is an equilibrium step, and for all subsequent cycle, this is equal to 0, right. So, we can solve this using the same solution procedure that we have developed and called it simplified method 1 in the lecture number 54, okay, that is the previous lecture. Now, what about work control? So, work control means, let us say, if I go back to this previous idea of generalized displacement control, I said this Bg can be a suitable vector, a convenient vector, right. Now, let us say if I take this Bg is my external incremental load vector, which is the load proportionality factor, which is incremental, times the reference load. If I do that, then if I write this generalized displacement is equal to Bg transpose delta r. Now, Bg is equal to that. So, if I substitute, then what is this quantity? Reference load transpose incremental displacement. So, this is basically work increment, isn't it? So, I can now say develop an work control technique for the jth iteration, the work increment, okay, which is delta Wj. That means this quantity is no longer a displacement, but a work, okay. So, delta lambda j r reference transpose, and then again I am writing this quantity as a summation of the displacement increment due to reference load and displacement increment due to the unbalanced force vector, right. So, for the first increment we specify what is my work increment. For all subsequent increment, work increment is 0. So, from here I can calculate what is delta lambda, which is this equation just from this, right. And note for the first one that this unbalance is equal to 0, that means this quantity is almost equal to 0. So, for the first iteration this is 0. So, this is my expression for delta lambda, and for the subsequent iteration for j is greater than 2, this will give you that equation. So, that is a work control technique. Okay. Notice what is the difference between the method 1 or simplified method 1 versus generalized displacement control and work control. Well, in the latter two, generalized displacement control or work control, we are actually including all the degrees of freedom. Whereas, in method 1 or simplified method 1, we have only one degree of freedom that is being controlled. Okay. So, for more details about work control, you can look at this book. Okay. So, with that, let us summarize what we have done in this lecture. We have discussed briefly about the pushover analysis, which is a nonlinear static analysis, and we have gone through the theory how to do nonlinear static analysis using displacement control technique or generalized displacement control technique or work control technique, and we have identified some limitation of the displacement control technique, that you have to choose the degree of freedom. If you are controlling the DOF at a node, okay, then you have to choose it in such a manner that displacement of that DOF is increasing monotonically, otherwise it will not work for a snapback kind of problem. Okay. We have also discussed about generalized displacement control, which I am calling method 2, and also the work control technique, and we have seen some examples of 3-member arch or truss, okay, that shows both snap through as well as snapback behavior, right. So, in the next lecture what we will do, we will talk about the constant arc length methods. Okay. So, these are some of the references that I have used in preparing this lecture material, okay, and these are the remaining ones. Okay. With that, thank you and see you in the next lecture. Okay.